Here we're going to define the motion, that is the position, velocity, and acceleration of a particle that can freely move about in a 2D plane. So I want you to consider a particle located at point P. In order to define this particle's location in the 2D plane, we first have to define a reference frame, which in this example I'm going to call frame A, which is defined by an origin point, which we'll call O, and two perpendicular unit vectors, which we'll call A1 and A2. Now the location of point P in frame A is defined by the following vector, which is drawn from point O, the origin of frame A, to point P. And this vector here is what we will refer to as the position vector. And the notation that we'll use to describe this position vector is as follows. We'll always use a lowercase r to denote position. And because this is a vector, we're going to use the underbar. And because this vector runs from point O to point P, we're going to write up here OP. So again, just to write this out, ROP in terms of notation indicates the position vector from point O to point P. So this vector as drawn right here is ROP. So now that we've drawn this position vector and established the notation, we have to mathematically describe this position vector. Now the position vector is two-dimensional because we're working in a 2D plane. And that means we have to describe its the magnitude in two directions. And the two directions that we're going to use are A1 and A2. So you can think of it as we're breaking our position vector down into two components, one in the A1 direction and one in the A2 direction. And we're just going to call assume we know that the magnitude of this vector here is x, and we're going to call the magnitude of this vector here y. And with that, we can now write out the position vector as x times A1 plus y times A2. And this right here is a mathematical description of our position vector, which has two dimensions. So now we're going to go ahead and calculate the velocity of point P in frame A. And as you may recall, the velocity is the time derivative of position, so how that position vector changes over time. So in terms of notation, we're going to use a capital V in order to indicate velocity and an underbar to indicate vector. On the right-hand side, we are going to put a P to indicate that we're taking the velocity of point P. And on the left-hand side, we're going to write A to indicate that we're taking the velocity of point P in frame A. So just to spell that out one more time, because this is, again, the notation that we'll be using throughout the class, what I've written here is the velocity vector of point P in frame A. And so to define velocity in terms of ROP, we take the time derivative, and we're going to write this out as follows. So we have our velocity vector. We're going to take the time derivative d dt of ROP. And in terms of notation, I'm going to add an A up here right in this top corner, right by my writing of ddt, and that is to indicate that, in fact, our position vector is defined in frame A. So just to write this out, we can now say that we are taking the time derivative of x a1 plus y a2. Now, in order to calculate this derivative, it's worth remembering that when you take the derivative of a times b, this equals the derivative of a times b plus a times the derivative of b. And so with that in mind, we can actually write out this derivative as the time derivative of x times a1 plus x times the time derivative of a1. And now we move to the second term here, which would be the time derivative of y times a2 plus y times the time derivative of a2. Now, one thing that I did not mention is whether this reference frame is dependent on time. In other words, is it moving? We know, or we're going to assume, that our point P is moving within a frame, meaning that its position is going to vary with time. But what about frame A? It's very possible that it can. You can have a reference frame that moves over time. In this case, we are going to assume that it is fixed. In other words, it's not going to move. And what this means is that when we look at if we were to consider the time derivative of a1, that is going to go to 0, meaning this whole term cancels out. And the same thing with y2. If we have a fixed reference frame, a frame that is not moving, this derivative and hence this whole term goes to 0. And with that, we can then write out our velocity of point P in frame A as the time derivative of x times a1 plus the time derivative of y multiplied by a2. There you have it. All right, so I've cleared out a little space, and now we have plenty of room to go ahead and calculate the acceleration of point P in frame A. So just for reference, I'm going to go ahead and write out again the position vector and our velocity vector for point P in frame A. And so we're going to use very similar notation for acceleration as we did in velocity. The only real difference is that instead of a capital V, we're going to use a lowercase a to indicate acceleration. But we're going to similarly put a P in the top right corner to indicate that we're taking the acceleration of point P, and a capital A on the left to indicate that we're taking acceleration of point P with respect to frame A. Just like velocity is the time derivative of position, acceleration is the time derivative of velocity. Don't forget that little A for frame A up there. So we'll write this accordingly. And now we can actually go ahead and write out the velocity vector as x dot a1 plus y dot a2. And we're going to use the same product derivative of product rule that we did before. And so just to write that again, we have the time derivative of a times b is equal to the derivative of a times b plus a times the time derivative of b. And so with that, we can write out that the time derivative of x dot, which is x double dot times a1 plus x dot times a1 dot plus y double dot a2 plus y dot a2 dot. And again, we said that this is a fixed reference frame, it's not moving, so these terms go to 0, and now we can write out the acceleration of point P in frame A as x double dot a1 plus y double dot a2. And so there you have it. Our three equations. The first is position of point P in reference frame A, and then we have our velocity as shown here. And finally, we have our acceleration.